Chapter 27, lesson number 5. Now that we have formulas for both constructive and destructive, the question is, what does that actually look like? Now, if I were to take the slits, hold them up to my eye, and then look at various objects, light bulbs for example, what I would start to see are bright and dark areas. You know when it strikes here, we knew that it was bright because it was a whole number wavelength. But if I change the angle a little bit, isn't that pathway going to be a little shorter, and then I'll end up with a half? And then when I do it again, it'll be bright again, and then dark. So what I'm going to see is a corresponding pattern when it's one wavelength away, half a wavelength, one wavelength, half a wavelength, one wavelength, corresponding bright, dark, bright, dark, bright, dark, bright, dark. So it's interesting when you look at lights through slits, you actually see patterns of stripes, bright, then dark, then bright, then dark. Now if you take your fingers, it really depends upon your personal structure. Alright, if I hold my fingers up like this, next to each other, I can form a little bit of a slot, a space, slit between my two fingers. Now if I hold them up to the light, and I squeeze my fingers together just right, I can make the slit open and close. Just like if you squint with your eyes. If I get them just right, I look in there, I can actually see bands of bright, then dark, then whatever. So it doesn't take sophisticated equipment to actually see these effects of bright, dark, and whatever. Two fingers, hold it up to the light, and you can actually see the stripes between your fingers. Alright, now we do have some good equipment here. These have been left to us since 1958, and we're still using them. It's too bad you can't be here today because it's very interesting to turn the lights out in the room, then actually see these interference patterns of bright, then dark, then bright, then dark, actually through them. So I've tried to draw them on the board. This represents waves. This is the bright one, then it's dark, then it's bright, but notice that it's not as bright as it used to be. Then it's dark, then it's bright again. So let me write this out for us. All right. The center, of course, is going to be bright. Then we have an area of darkness. It's bright again, but remember, not as bright, seems to fade away, and then dark, and then bright again, but once again not. This pattern repeats itself on the opposite side as we pass through that middle area. Isn't it going to be symmetric on the opposite side as well? So we're going to have areas, again, that would be dark. This is a bright area, not as bright as the center. Dark again, then bright. So we're getting these stripes of alternating bright, dark, bright, dark, bright, dark, bright, dark. Trying to say that fast, not going to be easy. All right, now that we've established that pattern, let's see if we can actually do some math for this. So as we look at these areas of brightness and darkness, all right, we can actually start to measure some things. Now what I'm going to do is draw a line along the center like so. And this line goes back, it's just a reference point, and it's going to go back to where the slits themselves are actually at. So if I look here, I'm going to put my slits back in here. And there they are. Okay, like that. Alright, now if I draw some lines, I can also draw lines to various points. So I'm going to draw a line, and that line wasn't so great. Alright, let's try this one. And I'm trying to go to the next bright area right over here. So if I look, we've got a bright area here and a bright area here. Now the distance between these two areas I'm going to call x1. x1 is the distance from the center out to the first bright peak. It's a distance that we can actually measure with a ruler if we put it on a screen. So we've now got a nice triangle. The distance from the slits over to where the screen is that we're watching these bright and dark areas, we'll just call L. Alright, if we look at this trigonometrically, we have an angle in the corner like this, so we can say something along the effects that tan of the angle is equal to opposite, which is x1, divided by the adjacent side. So I think everyone would agree. We've got a nice triangle here, a nice angle. This distance here vertically is the distance from the bright center out to the next bright one here, and we can use tangent. Now, if we want to cheat a little bit, this is exactly true. If I keep the angles fairly small, this is approximately true. I know it's a little bit of a lie, but the sine of the angle, if the angle is small, is approximately equal to the tan of the angle. So what I'm going to do is, that's supposed to be an approximation sign. All right, look at that nice little wavy thing like so. And this formula is approximately correct. So I'm going to go with this one as long as I don't need excessive accuracy. All right, when I go back to my original formulas now, as I look through this particular one, we know that d sine of the angle, if I want constructive, bright lines, which I do have right here, is equal to m divided by m times lambda, this being the order. Can I replace now sine theta with x divided by L? So now I have d x divided by L equals m lambda. All right, now, if I know this particular formula, it's an approximation and it's pretty good. All right, I can now use this to measure things. All right, now, using this particular formula, is it possible to know the distance between the slits? We call this d. Well, of course it's possible to measure the distance between the slits. I'm the one making the slits, so when we manufacture this, we actually know that value d. X, the distance between the bright one and the next bright one. Well, yeah, once again, that's something that I can actually see. When I project that on the screen, I can actually see the bright, dark bands. So I get a ruler, put it on there, all right, and I measure the distance from here to here, like so, and I can actually calculate what x is. L is the distance from the screens, from here out to here. I can use a ruler to measure from the slits to the screen itself and get that measurement. M, we're going out to the very first one, so M here is 1. So if I look here, M would be 1 in this particular case right here. Now I can calculate the wavelength of the light. This is a famous experiment that was done by Young, and it's the way that we actually measure the wavelength of light.